at the center of our uniform ring, we'll have zero gravitational field intensity because of the symmetry of the geometry. Now, let's see if I change my position of concern. Now, the position is at the axis of the ring, but at a slight distance away or at a significant distance away from the center of the ring. By which I mean that it's not at the center of the ring, it is on the axis. It could be at any of the points on the axis. Now, what will be the value of gravitational field in this circumstance? To calculate this, just look at this diagram and try to visualize this with the same concept which we developed in the previous case. Small element masses and the distance of the element masses with the point in concern, right? So if I think of the geometry, what will happen here is this thing can be thought of as that there's a point mass over here, dm, and this point mass dm is separated by my point with some distance which can be calculated in this way. This thing over here, just check here. This is the radius of the ring, which is a, and this thing over here is essentially the separation x away from the center of the ring. So this distance over here would be square root of a square plus x square. Now, the direction of gravitational field, it would be towards the dm, so it would be towards this line, right? You can also check this in this diagram. It would be towards this line. Now, similarly, I can construct various dms, and all the dms would have gravitational field towards this direction, and it would form something like this, right? Now, if you visualize this diagram, what will happen is, just think of this angle as theta and divide this force into two directions, this value and this value. These two forces are essentially the components of this gravitational force in two directions, and similarly I'll have a dm just below this, and that dm would have a force in this direction, right? Now this force would have two components, one here and one in this direction, right? Now these two guys would cancel each other out, right? And effectively what I'll have is a situation in which all the dms are getting cancelled out in this direction, but the value of force in this direction are getting added up. So for every dm, this force would be added up. Okay, so let's calculate the small force due to dm. df. This df would be essentially equal to g times dm into the mass of point mass here divided by separation square. Now, as we have discussed the technique in the previous situation, that we don't need to bring a point mass m. What we need is just a 1 unit mass here and calculate the force, and that force would essentially be your gravitational field 2, right? So here if we calculate df, this also would be my dE value, right? So for now just write df and we'll rationalize this thing later. Why df is not equal to dE or something like that. Now g into dm upon square of this value, which is a square plus x square. Now this df has two components, one in this direction, one in the perpendicular direction. The perpendicular direction one would be cancelled out by each other. I need this direction, which is df cos theta. So df into cos theta would be equal to g dm by a square plus x square. In this triangle, right angle triangle, the value of cos theta would be simply x upon this quantity. So like that, x upon square root of a square plus x square. Now this is the small value of gravitational field in the x direction. If I add the contribution of all the dm's, right, I'll have the net gravitational field value, which would be equal to integration of this. Now in here, we just check the idea. G, this value, this value, this value, nothing is dependent on my dm. So this dm thing comes out, and if I integrate that dm, it would essentially be simply capital mass m. So my value of electric, or rather gravitational field, would be gm by a square plus x square. Now here I have 1 as my exponent. Here I can think of half as the exponent. So this is 3 by 2 into x. So this is the gravitational field at a point on the axis of a ring, right? Now let's say I try to correlate, or rather try to have some kind of idea that is this value valid for all the cases or not. Let's just check it. I know that at the center of the ring, my gravitational field value would be equal to 0. So put x equal to 0. What you will get is E is equal to 0, because the numerator has x, which confirms my belief that at the center of a uniform ring, my gravitational field value would be 0. Let's further carry on our conversation on the calculation of gravitational field intensity values. Next arrangement which we'll discuss is a hollow sphere, and let's say I have to calculate gravitational field intensity at two types of positions, one inside the hollow sphere and one outside it. Now Newton gave a lot of time to understand this basic idea that for the calculation of gravitational field intensity or gravitational force due to a hollow spherical mass or a solid spherical mass essentially can be thought of or treated as a point mass concentrated at the center of the sphere. See, even we can carry on our calculus discussion and arrive at that result, but that won't add much to our analysis. That would be needlessly mathematical in approach and won't solve much of our physics purposes. So let's just think of this idea that if we have a hollow sphere, I can think of that hollow sphere as a point mass concentrated at the center of the sphere. And let's carry on a discussion from that. I'll also give you an idea why it is kind of logical. Let's say you have a hollow sphere here of capital mass m and a as your radius. Now, if your point is outside this sphere at some distance r away from it, r from the center of the hollow sphere, I can think of such points over a region, hollow spherical region of radius r, by which I mean this sphere is symmetrical in nature, right? So if I take this as my point of concern, there could be a similar point at r separation away from the center of the hollow sphere, here, here, or here, in a spherical region, right? Which means that all of those points are identical, which is similar to the idea of a point mass. Even if you keep a point mass and take an r distance away from that point mass, the gravitational field value would be same for all the r distances. And locus of all that r distances away from that point mass is a sphere essentially which means that point mass treatment is similar to the spherical mass treatment for an outside point, right? So the value for my gravitational force can be calculated very easily. So what I'll do is I'll bring a unit mass at this point of concern and find out the value of force, and that would give me gravitational field intensity, which would be E would be equal to G times M upon capital R square. Now, let's say you want to have the value of gravitational field intensity inside the hollow sphere. Again, I'll have to test your capacity of taking things for granted, but you have to take this from me, that if you go inside the hollow sphere, what happens is there are masses, point masses, which would, on this half essentially, which would attract the point mass on this side of the sphere. And there would be point masses which would attract this point mass towards this side, which means there are two directions for the forces. So I could get a net zero force, which means I could have a zero value of gravitational field intensity. If we do mathematical analysis, even that comes true, right? So I won't needlessly bother with the mathematical calculation, just take it from me that inside a hollow sphere, the value of gravitational field intensity goes to 0. So what I can infer from this is that the value of gravitational field at an inside point is 0, which means R is less than A, and if R is greater than A, which is an outside point, it would be Gm by R square. Now I can put the inequality here. Why here? Because if I am A away from the center of the hollow sphere, essentially I can think of the hollow sphere concentrated at the center of the hollow sphere, right? Which means this thing is valid. Now, if we plot a graph of gravitational field intensity versus R, I'll just have to draw this function, which should be like this. This is your R value, this is your E value. Till A, till the radius of the hollow sphere, your gravitational field value would be 0. But after it, what happens is it follows this law, right? Which is here. This value is your Gm upon A square. I have used the value of R equal to A here. And this falls like this. But it never goes to 0 because it would go to 0 only for the case of R equal to infinity. So it tends to 0.